Hi, and welcome to Mr. Carroll's Classroom. Today we're going to explore how to solve exponential and logarithmic equations, specifically using the inverse operations. So let's go ahead and get started. Okay, so first I want to talk about in mathematics in general, whenever you have any type of equation, the first thing you really want to do is you want to isolate the most complicated operation. Now, you might have many complicated operations in any given equation. Just go ahead and find the most complicated one you have and isolate it, get it on one side of the equation, then apply the inverse operation to both sides to get that one complicated operation to cancel. And then go ahead and see where the chips fall, basically, and go ahead and identify the next most complicated operation and repeat the process. Isolate it, take the inverse to eliminate it. And you just continue to eliminate the most complicated operations until hopefully you can get it down to just your variable on one side and some kind of answer on the other side. So all right, so let's go ahead and take a look at what that might look like. So here are some examples of three examples here of just random equations. This first one here, if we identify the complicated operations, this first one has a binomial squared, the second one's got a radical in it, and the third one actually has an exponential in it, which is what we're gonna part of what we're gonna deal with today. But ultimately, these are the complicated operations here, and so what we want to do is isolate these. So we will get them onto one side. Isolating means move it algebraically to get it all on one side. Then we simply can apply our inverse property, whatever, or inverse operation, whatever that happens to be, the opposite of that complicated operation, in order to eliminate that. All right, so that's essentially what we do in all of mathematics. And for today, we are specifically going to be applying this to exponentials, which we have an exponential here on the left. And I did leave a little bit of room in here, and I'll talk about why I left that room in there in a second. But on the right-hand side, we have a logarithm, which is actually it's actually the same exact, technically speaking, these are the exact same equations here. It's just that one of them is expressed as an exponential and the other as a log. So right away, these are already isolated, meaning the complicated piece is on one side, which means that we can apply the inverse property. So let's go ahead and do that. So on the left-hand side, what's the inverse of base 2, an exponential of base 2 to the x, meaning we're gonna continuously multiply over and over and over again by 2, while dividing by 2 repeatedly, or log base 2, which is dividing by 2 repeatedly. So over here, we can see that we are both multiplying by 2 over and over again and dividing by 2 over and over again. So those two operations are going to completely cancel each other out, leaving us just with x. Okay. Now on the right hand side here, we have log base 2 of x. Well, the opposite of repeatedly dividing by 2 is repeatedly multiplying. So that is an exponential with a base 2. So 2 to the power of something. So I'm going to take 2 to the power of both sides of this equation here. Okay, and again, right here, I'm repeatedly multiplying and dividing by 2 simultaneously, so this x is going to pop out of here. Now, whoops, hang on one second. We'll talk about restrictions here in a second. When we get after we get the x to pop out of here, then we can simply evaluate these the other sides. However, I do want to point out that having the same base is extremely important here, right? If this is base 2, but I take log base 3, for example, these do not cancel out because I'm repeatedly multiplying by 2, but I'm repeatedly dividing by 3 in that case, if it was a base 3. So it's really important that our bases do match, okay? All right, so our answers here that we get are 2 is equal to x, or x is equal to 2. That's because log base 2 of 4 is equal to 2, meaning how many times do I divide 4 by 2 to get back to 1? Well, I have to do it twice. So, all right. And over here, I have 2 to the 4th power, which is 16. 2 times 2 times 2 times 2, which is 16. And so you might think, okay, we're good. We're going to go ahead and circle these answers. But one other thing that we always have to do in mathematics, no matter what, is you should really take a look at your solutions and look at the original equations and just check, are there any restrictions that need to apply? All right, so let me go ahead and take out my work just so that way it's not uh, it's just out of the way. But what are our actual restrictions here? So the restrictions for this one on the left, well, there actually are no restrictions. X could be any positive number. That's obvious, right? I could take 2 to the 5th power, 6th power, whatever. It could be 0, right? Anything to the 0 power is 1. And it also could be negative, like 2 to the negative 2nd power is going to be 1 over 2 squared, which is 1 over 4. So there are no restrictions on the left-hand side. However, with logarithms, there are restrictions. In fact, this x value, or whatever's inside of the parentheses of the logarithm, it has to be a positive number. And it also cannot be 0, and it cannot be negative. All right, so anytime you get an answer that is 0 or negative, then that answer does not exist. That is an extraneous solution. It is not an actual solution. Okay, and the reason for that, like imagine if this was log base 2 of negative 4. That means how many times would I divide negative 4 by 2 to get back to positive 1? Well, you can't, because I can divide negative 4 by 2 an infinite number of times, and it's still going to yield a negative number. So I'm never going to get to positive 1, right? So I can never have a negative in there. Okay. All right. Anyways, so let's bring our work back here. And so we can then go ahead and say, well, this one definitely works. X is equal to 2 because there are no restrictions. And over here, yes, 16 is a positive number, so it does check out. All right, that is a solution. All right, now before we actually apply these to real problems, and we're going to do like 4 examples here, let's just remind ourselves of the exponential and logarithmic rules. These are the basic rules. There are a few more trivial rules, but the basic ones are the ones that we really need to know about. And the reason why has to do with us combining terms. So for example, if I had something like this, like some base to the power of m times another, times the same base to the power of n, well, I can combine those into one base to the power of m plus n. That's going to be really important because when we isolate, we want to make sure we have just one exponential on one side or one logarithm. Like over here, if I have 2 logarithms with the same base, log base b of m plus log base b of n, then I can combine those into one logarithm base b of m times n. That's the product rule. So we have the product rule, the quotient rule, we have the power rule for all of these. And then we also have something that can be quite important, which is the change of base rule. When we start to solve some more complicated equations in a future lesson, then you're going to have to utilize this property just in your algebra alone. However, for today, you might have to use this depending on your calculator. So let me go ahead and show you what I mean by that. Actually, let's cover the change of base rule real quick. So log base b of m is equal to log base anything else of m divided by log of that same base of b, so c being some other base. So you can actually take one logarithm of a base that you don't like, essentially, and you can convert this into another base c, whatever you want it to be. And the reason why that's actually quite important is because if I bring up our calculator, this calculator can actually do any base. However, many calculators cannot. In fact, let me just show you the buttons on this calculator and buttons that are on almost every calculator. So right here is the logarithm, and this is the common log, meaning this is log base 10. Okay? And by the way, you can also do second that button, and you can take 10 to the power of x. Down below it, we have ln, or the natural log, which is log base e. And of course, above it, we have e to the power of x, the exponential equivalent. All right. We also, it might be worth noting here that we do have this constant e over here that we can always use. It's right underneath the pi above it. Okay. But most calculators will have this. Not all calculators will have what I'm about to show you, which is the ability to put in any base. So in this particular calculator, you can go to Math, and if you go under the Math subsection here, all the way down to the bottom, the second from the bottom, we have log base. And if you hit enter, then you can see you can put in any base. So for example, if I have like log base 2 of 4, then this should evaluate to 2. Let's see if it does. And there you go, it does. Okay, so those are the buttons that we're going to end up using to solve these types of problems if you have to use a calculator. Okay, so let's go ahead now and whoops, we are going to do some examples. Okay, so for this first example, we're going to, and by the way, so there are 4 examples total. The first 2 are going to be exponentials. The second 2 are going to be logarithms, and they will each increase in difficulty. Okay, so this first example we have, grab my pencil here. All right, we have 39 times 10 to the 4x is equal to 390. So number 1, let's go ahead and identify the complicated operation here, which is definitely 10 to the power of 4x. In fact, we need to get this x out of the exponent, essentially, is what we're trying to do here. All right, so let's go ahead and isolate it. That's step 1. So I'm going to divide both sides by 39. And so on the left-hand side, I will end up with 10 to the power of 4x is equal to, and I have 390 divided by 39 is 10. And technically, right now, I could actually kind of look at this. I actually already know the answer is going to be 1/4, and we're actually going to learn how to figure that out in a future lesson here. But for now, we're going to continue, and we're going to use our inverse properties to solve, because applying inverse operations will always work no matter what. What I just did in my head may not always work. Anyways, so and actually, let me put a little bit of space over here, because I need to do the opposite of 10 to the power of something, which is log base 10, right? In order to wipe this out, I'm going to take log base 10 of both sides. And so these are going to cancel, repeatedly multiply and divide by 10 at the same time. So the 4x is going to pop out. And that is equal to log base 10 of 10. Well, how many times do I divide 10 by 10 in order to get back to 1? Well, that's just 1 time. All right, and here you can see if I divide both sides by 4, then I get x is equal to 1/4. Now, I don't want to circle this yet. I want to go back and check, are there any restrictions? Well, in exponentials, no, there are no restrictions here. And so I can go ahead and say, yes, this is my answer. X is equal to 1/4. And then finally, I'm just going to take a look and do this math in my head, because this one's pretty easy to do. 4 times 1/4 is 1, and 10 to the first power is going to be 10, which means that I end up with 39 times 10, which is 390. So yes, this does check out. All right, let's go ahead and do a slightly more complicated one. So in this case, I have 7 is equal to e to the power of 2x times e to the power of x minus 3. And don't get freaked out by e. That is not another variable. Remember, that stands for an actual number. That is Euler's number, that 2.7 blah, 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 blah. Similar to it's an irrational number, kind of like pi. But anyways, the issue is I have 2 of these, right? Well, I can combine these because I want to isolate it and I want to combine it into one exponential, right? And I can combine these because if I have any base, right, to the power of m times the same base to the power of n, then that's equal to that base to the m plus n, right? That's one of our rules for exponentials, one of our properties. So let's go ahead and do that. And actually, at the same time, I'm going to go ahead and add this 3 to the other side. So I'm going to do that as well. So I end up with 10 is equal to, that would be e to the 2x plus x. And of course I can combine those. So that is 10 is equal to e. And I'm going to put a little space in here because I know I'm prepping this, right? I have an exponential, so I'm going to have to take a logarithm. But anyway, that's e to the power of 3x. All right, now, one thing I want to mention here is that this is e to the power, an exponential with a base of e, right? So I want to take log base e of whatever. But I want to note that log base e is commonly written as ln, or the natural log. These two expressions here are equivalent, okay? Log base e is the same thing as ln. Now, if that confuses you, then forget about ln for now anyways. It is expected that you know what ln is, but at least in the beginning, you don't have to use it. You can literally just always use log base e and you will get the exact same answers, okay? But I am going to go ahead and use ln. Again, if you're not comfortable with that, then just use log base e. So I'm going to take log base e, or the natural log of both sides. Hang on one second. It's kind of hard to... Well, it doesn't really line up, but that's okay. All right, so I'm going to take the natural log of both sides. And so on the left-hand side, I'm just left with ln of 10. Now on the right-hand side, log base e of e cancels out, or the natural log of e cancels out, just leaving us with the 3x. And now in order to solve for x, I'm going to divide both sides by 3. So that is the natural log of 10 is equal, divided by 3 is equal to x. Now, if you wanted an exact solution, then this would be your exact solution. We don't have any restrictions here because these are exponentials in the beginning. However, if the problem asked you to maybe like round to the nearest tenth or something like that, how would you actually do that? Well, let's go ahead and bring up our calculators just so we can get some practice with these. All right, and so I'm going to plug in the ln of 10, the natural log of 10, divided by 3, and I get an answer of 1.2, so on and so forth. Now, oops, hang on one second. I have an extra parentheses in here. My fault. Hang on one second. Let me just make sure that we're okay. Delete that. Ah, there we go. I thought that number looked a little bit off. Okay, so actually our solution is 0.7675. And it just goes to show, make sure you have your correct parentheses. I'm surprised they let me get away with this actually, because I had two left-sided parentheses and then only one on the right. But anyways, so the ln of 10 divided by 3 is 0.7675, so on and so forth. Now, let me just prove to you that the ln is the same thing as log base e. If I go to math, and I go down to log base, then I can put second e in here for my base, and that is log base e of 10, all divided by 3. And let's just see if I end up with the exact same thing. And you can see I do, 0.7675, right? So on and so forth, right? So the natural log is the absolutely identical to log base e, okay? All right, anyways, let's continue on to logarithms now, or starting with a logarithm. Okay, so for this problem, we have log of x. So actually, I'm missing a base here. I left that out purposely. Log of x plus 3 is equal to 5. And so the reason why I left this out is because whenever you see ln, you could write log base e, or if you just see log, then that is the common logarithm, meaning this is actually log base 10. And actually, let me use a different color just to pop that in here. And again, if it makes you feel more comfortable to put that base in there, then put it in there, right? And then once you get really good at these, then you can just still do the math without it, just understanding that it's a base 10. All right, so of course, our complicated thing here is this log base 10 of x. So I want to isolate it. So I'm going to subtract 3 from both sides. So I get log base 10 of x is equal to 2. And maybe I'll make a little bit more room over here. All right, so now what I need to do is I need to get rid of this now that it has been isolated. And in order to get rid of a log base 10, I need to take both sides to the power, or 10 to the power of each side, right? So that is 10 to the power of the left side and 10 to the power of the right side. All right, and so on the left-hand side, I'm both repeatedly multiplying and dividing by 10 over and over again, so that x in parentheses is going to just pop out of there. So x is equal to, and that is 10 squared, which is 100. All right, now check your restrictions here. That would end up being log base 10 of 100, which, by the way, we can actually check this. So log base 10 of 100, how many times do I divide 100 by 10 to get back to 1? Well, that's twice. So this would evaluate to 2 plus 3, which is equal to 5. And so we are all good here. Both this would not give us a negative inside that logarithm, and it actually checks out, right? Okay, so let's go ahead and do one more problem. And this one is going to be slightly more difficult here. And although there's not that much going on, but what you do notice is that you have two complicated terms here: log base 2 of x and log base 2 of x. So what I'm going to do is I'm going to move those to the same side and then attempt to combine them with one of our logarithmic properties. So let's go ahead and see if we can do that. All right, so I'm going to subtract, I'm going to add this one over, this log base 2 over. So that I end up with 4 is equal to log base 2 of x plus log base 2 of x. And at this point in time, you actually can go a few different routes. What I'm going to do is I'm going to say, well, I have log base 2 and log base 2, and these are being added to each other, so I can use my product property. So I can multiply the two insides here, this x and this x, all right, and combine them into one logarithm. So I end up with 4 is equal to log base 2 of x times x, which is just x squared, okay? And then, let's see here, we're all ready to go. What I want to do now is I want to get this x squared out of here. So I want to remove this complicated thing, this complicated log base 2. So I'm going to take 2 to the both sides, right? The opposite of log base 2 is 2 to the power of. So I have to do it to both sides. So on the left-hand side, 2 to the 4th power. Well, that's 2 times 2 times 2 times 2, which is 16. And over here, continuously multiplying and divided by 2 will cancel out, and that lets this pop out of x squared. All right, now, this is a little bit more interesting of a problem. So I have 16 is equal to x squared. So I have to continue on here, right? In order to get just x out of here, I got to take the square root of both sides. But be careful. Remember, since I'm taking the square root of an variable squared here, then that means I have to say plus or minus. So I have plus or minus 4 is equal to x. Okay, so I actually got two solutions here, and let's go ahead and check if they work. So I have x is equal to 4. Actually, let's move this over here. So I have x is equal to 4, and x is equal to negative 4. And so let's go ahead and we'll check our restrictions. So first of all, if I plug in positive 4, well, I'm plugging in that here and here, and that is the log of a positive number. So that one definitely works. Check. Right? This next one, though, x is equal to negative 4, I can't have that because then I would have a negative, the logarithm of a negative number, and we cannot have that, so this does not work. Okay? Now, one last thing I want to talk about is there are many, many routes that you can take to solve these types of problems. In fact, many of you may have, at this point, done something different. When you had 4 is equal to log base 2 of x plus log base 2 of x, well, these are the same exact terms. It's kind of like saying m plus m is equal to 2m, right? If I have 2 of these terms, then I could rewrite this as 4 is equal to 2 of those, 2 times log base 2 of, what is that, x, right? And I want to show you that this is actually equivalent. You would end up getting the exact same thing. And why is that the case? Well, we have the power rule. Remember, the power rule says that if I have any power up here, like if I had a 2 up here, then I can move that back and forth, right? So this is equivalent to 4 is equal to log base 2 of x. And it doesn't matter if you put the 2 inside or outside the parentheses, but I'm going to put it on the inside. You end up with 4 is equal to log base 2 of x squared. And lo and behold, that is the exact same thing that we ended up with down here. 4 is equal to log base 2 of x squared, right? So there are many different routes. Just make sure you know you're solid with your properties for both exponentials and logarithms. And again, it's the same procedure over and over. Isolate the complicated piece, and then go ahead and apply the inverse to eliminate that complicated piece, and then go ahead and move on to the next complicated one until you get to the point where you just have your variable on one side. Okay? All right, guys. Hopefully you found this helpful, and now you kind of know why you've been spending a lot of time learning how to manipulate exponentials and properties using those rules. Well, because we have to have that solid foundation in order to now solve for these types of equations. Okay. All right. Again, hopefully you found this helpful, and I hope to see you in the next one. Bye now.